Hey, what's up, guys? What's up, guys? So in the previous video, that we talked that the proof square root 2 is irrational. Use the infinite descent. Okay, so if you haven't seen the previous video or the proof of infinite descent list, I will put the link below, so you can check out the infinite descent links. The list of the infinite descent method. Right, there's a easy example like square root of 2, and what we want to talk today is the square root of k, and another some difficult example like the Fermat-Less theorem. The Fermat-Less theorem for n equals to 4 special case, and we will have some much difficult examples in the future. Okay, so today let's talking about proof the square root of k is irrational. Irrational by infinite descent. Okay, I want to say is that right, so k is not perfect square. Not perfect square. Okay, so perfect square means that k is u square for some u, which is an integer, right? So by the way, k is some positive integer. So k is a positive integer, which is not perfect square, and we will prove it is irrational. Okay, so the stupid example everyone knows is square root of 2, square root of 3, square root of 6, 7, 8, and okay, so so I will leave the exercise for you to prove that use your general the junior high school idea, right? So in a junior high school, you can easily prove the square root of 2 is irrational, and you can prove the square root of 3 is irrational. And finally, you can generalize to prove that the square root of p is irrational for p is prime, right? And once you prove this, then you can easily prove like more general, like so. This is a question that how do you prove the square root of 6 is irrational? So let's assume, so you can write the square root of 6 as p over q, right? And let's say 6q squared is p squared. But you cannot say q. You cannot say so let's see, right? So from here that you can say, you can assume that p, q are coprime to each other, and you get 6q squared equals to p squared. And from this you can say, oh, 2 divides p, right? Right, and so you get a p equals to 2k or something, right? And so you get 6q squared equals to 4k squared. So 2 and 3, and you know that, so now 2 must divisible by 3 or divisible by q, right? So the only possibility is that since 3 cannot divisible by 2, so the only way is that q is divisible by 2, right? So q can equals to 2u, right? Which you know that this and this contradict. Okay, so you can argue that so now once you prove a square root of 6, then you know how to prove that composing pq, which q is not the same as p. Then you can use the general idea to prove that if k is not square root of not square free, then the square root of k must be irrational. So this is the common idea, right? But now we need to use a more difficult one. So our goal is to prove square root of k by infinite descent. Okay, so the idea is that I pick up q to be let's see, to be the largest integer smaller than k, smaller than square root of k. So which I mean what, right? So q is less than square root of k, less than q plus 1. Okay, so this should be very easy, right? So now our idea is that I want to write square root of k as m divide n, okay? Which mn are positive, both positive, and mn are coprime. Okay, and I pick, and I want to use I want to shuffle this m and n, and then I will get something, which is, let's say, m prime divided n prime, and such that m prime less than m, and n prime less than n. So this will lead to a contradiction, right? Because this for m and n are both positive subset of positive integers, so that cannot be infinitely smaller. So this is the proof of infinite descent, such that we need to find some m prime and n prime, such that the square root of k can be also expressed as m prime divided n prime, but it satisfies that m prime less than n and n prime less than n, and these m and n are both positive integers, so they cannot be infinitely smaller. So which is the idea of the proof of infinite descent. Okay, so hope you guys understand what I'm talking about. Okay, and this is a very a little bit tricky, but let's see. So let's m divide n, right? So let's see. So what should I do, right? So let's see. So I times m times the square root of k minus square root of k minus q. Okay, so notice that the square root of k minus q. Okay, so square root of k minus q should be what? Should be greater than 0, right? But less than 1. Okay, and the reason is that square root of k is bounded by a q and a q plus 1, right? So square root, so this is q, right? This is square root of k, this is q plus 1, right? So their difference is greater than 0, but less than 1. Okay. So we get, I can write n times the square root of k minus a q. Okay, so now everything is clear. I define m prime to be m square root of k minus q. N is n times the square root of k minus q. Okay, so the missing part is that this m prime, right? So this is m prime divided m prime, and we see that by definition, right? Since somehow they times something which is less than 1, less than 1. So that means we already have m prime less than m, n prime less than n. So the final things that we need to show m prime and n prime, since they are already less than original one, right? So our goal is to show m prime are what? Integers, right? Positive integers. And this is should be easy, right? So let's say m prime is m times the square root of k minus q. So m prime is m times the square root of k minus q. But I know square root of q is m divided n, right? So I can write m is n times the square root of k. Okay, so this is n. Okay, so maybe I write it. So I just write it as m square root of k minus mq, right? So mq is already an integer, right? Because m is an integer and q is an integer, and m times the square root of k can be written as n times square root of k. So it's n times the square root of k minus mq, which is nk minus mq, which is obviously an integer, right? Positive integer. Why positive, right? Because these are positive, these are positive. So I already know m prime is positive, so m prime is positive. Okay, and the rest is to show that n prime, which is n times the square root of k minus q, is also integer. And since we already know it's positive, so if it's integer, it must be positive integer. So n times the square root of k, let's see, n times the square root of k is m, right? So m minus nq. Okay, so everything is proof. Because m is integer and nq is integer, so their difference must be integer, and I already proved it's positive, so it must be positive integers. So now we have created m prime, which are both positive integers, and m prime less than m and m prime less than n. Right, so by the argument of the infinite descent, then the square root of k must be irrational. Okay, I just go quick because this is I think now you guys know a trick. So now we have some examples. That the first example is square root of 2 is irrational, and the second example is square root of k is irrational if k is not square root free. Okay, and also we proved that the famous one that which is famous in the n equals to 4 format. That's 0. Okay, now we will have more difficult infinite descent example in the future. So I will see you guys in the next video. I hope you guys subscribe to my channel.